Welcome back. In this lecture I shall discuss selection of inside design conditions based on thermal comfort criteria. The specific objectives of this particular lecture are to discuss need for selecting inside design conditions, define thermal comfort, write heat balance equation for human beings, discuss factors affecting thermal comfort, discuss thermal comfort indices, and finally present ASHRAE comfort chart and recommended inside design conditions for winter and summer. At the end of the lecture you should be able to explain the need for selecting inside design conditions, define thermal comfort, write heat balance equation for human beings, list factors affecting thermal comfort, list thermal comfort indices, and describe ASHRAE comfort chart and recommended inside design conditions for winter and summer. Let me give a brief introduction. Design and analysis of air conditioning systems involves the following steps: selection of suitable inside, outside design and supply conditions, estimation of required capacity of cooling or heating equipment, selection of suitable cooling and heating equipment, design of air transmission, distribution systems, controls, etc. And generally the inputs are the building specifications, its usage pattern, special requirements, etc. So these are the various steps one has to go through while designing an air conditioning system. Okay, so let us begin with the first step, that is the selection of design inside and outside conditions. In this particular lecture I shall describe selection of inside design conditions. Air conditioning is required, as you know, it is required either for comfort, that means comfort air conditioning, or for industrial use. For example, industrial use means it could be used in cold storages for preserving food products, or it could be used in process and manufacturing plants to provide the right conditions for the processes or the products being manufactured. The required inside conditions for industrial air conditioning vary widely depending on the specific requirements of the industry. So in fact there are many industries and many processes, many products being performed and all. So each product, each process requires different inside conditions. So you cannot have a universal criteria or universal value for inside conditions. Similarly for the cold storages, the required conditions inside a cold storage depends upon the type of product being stored, how long it is being stored, etc. Okay, so we cannot really generalize. So for these applications, that means essentially for industrial air conditioning applications, the inside conditions have to be chosen based on the specific requirement. Okay, when I say inside design conditions, what do we mean? What I mean is what should be the inside dry bulb temperature, what should be the inside moisture content. Inside means in the occupied space. Okay, so what is the dry bulb temperature in the occupied space, what is the moisture content in the occupied space, what should be the air velocity in the occupied space, right, what should be the level of purity required, etc. Okay. Unlike industrial air conditioning system, the required inside conditions for comfort air conditioning systems remain practically same, as this is related to the thermal comfort of the human beings. In fact, the human bodies are very much alike. So the required conditions for providing thermal comfort to human beings remain same irrespective of the location or type of the building or usage, etc. Okay, so we can have or we can formulate the required inside design conditions for comfort air conditioning systems. This is the topic of this lecture. So first let us define thermal comfort. What do we mean by thermal comfort? Thermal comfort is defined as that condition of mind which expresses satisfaction with the thermal environment. The definition is a bit vague because it is really very difficult to put it in words. Okay, so basically what it means is it is a state of mind when a user or when an occupant, if he feels satisfied with the thermal environment, then the environment is comfortable. Okay, so it depends upon the response of the occupant. So there is a lot of vagueness assigned to this. Okay, we will also see that the thermal comfort requirements vary from person to person. Okay, so it is not really possible to satisfy all the occupants. Okay, so this I will discuss a little later. The condition of thermal comfort is also sometimes called as neutral condition, even though strictly speaking they are not exactly same. But as far as we are concerned, the thermal comfort or neutral condition mean the same thing. A living human body may be likened to a heat engine in which the chemical energy contained in the food it consumes is converted into work and heat. Okay, so now I will explain what is the basic basis of thermal comfort and all. First, let us look at the human body. Okay, the process of conversion of chemical energy contained in food into heat and work is called as metabolism. Okay, so we know that all living beings, including the human beings, consume food. Food is required because this food is converted inside the body into heat and work. Okay, the work is used for doing some useful tasks, and the heat generation, the heat is required because, especially in human beings, we are warm blooded animals. Okay, our bodies have got to be maintained at some particular temperature. Okay, so the continuous heat generation is required. So the food we consume is utilized for these two purposes. So in this respect, a human body is like any heat engine. Okay, if you remember, we discussed heat engine, and I mentioned that a heat engine is nothing but a device which takes in some chemical energy in the form of a fuel and converts a part of it into work and a part of it into heat. Okay, so a human body is also like that. The rate at which the chemical energy is converted into heat and work is called as metabolic rate. Knowledge of metabolic rate of the occupants is required, as this forms a part of the cooling load of the air conditioned building. Why do we need to know about the metabolic rate, or why do we have to bother about the metabolic rate when we are discussing air conditioning systems? Because finally we shall see that whatever energy a human being is consuming in the form of food is ultimately rejected in the form of heat. Okay, so once it is rejected in the form of heat, it becomes a load, it becomes a cooling load on the air conditioned building. Okay, so if you want to estimate what should be the capacity of the cooling system, you must know what is the amount of heat rejected by human beings. That means what is the metabolic rate. Okay, that is the reason why we have to have information on metabolic rates. Okay. Similar to a heat engine, one can define thermal efficiency of a human being as the ratio of useful work output to the energy input. So we can also define thermal efficiency, and it is observed that the thermal efficiency of a human being can vary from 0% to as high as 15 to 20% for a short duration. Most of the time, for most of the activities, common activities, we find that the thermal efficiency of a human being is very low. Okay, it is almost close to 0%. But a human being can work with an efficiency as high as 20% for a very short duration. Okay, this is in a prolonged manner he cannot work with that kind of an efficiency, right. For most of the air conditioning calculations, we assume that the thermal efficiency is 0%. Okay, that means whatever is the metabolic rate is finally converted into heat. Irrespective of the work output, a living human body continuously generates heat at a rate varying from about 100 watts to as high as 2000 watts. So for a sedentary person, that means for a person who is sitting quietly, the heat rejection rate is about 100 watts. However, the heat rejection rate can be as high as 2000 watts when he is doing some strenuous exercises. Continuous heat generation is essential, as I have already explained, since the temperature of the body has to be maintained within a narrow range. The body temperature must be maintained within a narrow range to avoid discomfort, and within a somewhat wider range to avoid danger from heat or cold stress. It is very important that the human body temperature should be maintained within a certain range. Okay, if it falls below the particular temperature, or if it goes beyond a particular temperature, it could become very dangerous, it could become even lethal. Okay. Now studies show that at neutral condition, the temperature should be, the skin temperature should be about 33.7 degrees centigrade, and the core temperature should be about 36.8 degrees centigrade. At other temperatures, the body will feel discomfort, or it may even become lethal. For example, let me show this in a schematic. You can see here that when the temperature is 36.8 degrees centigrade, the human body is at a neutral condition. Okay. But when the temperature varies from about 35 to 36.8 or 36.8 to 39 degrees centigrade, that means in this range, a human being feels slightly uncomfortable. Okay, that means it's a slight discomfort is caused to the human being. But when the temperature falls below 35 degrees or goes above 39 degrees, that means in this region, it is observed that there is a major loss in efficiency of the human being. Okay, if he is performing any task, he will be performing it with very low efficiency. Okay, so from 31 to 35 and 39 to 43. But when the temperature falls below 31 degrees centigrade, or when it exceeds 43 degrees centigrade, it can become lethal. Okay, it may even lead to death. So you can see that effectively the temperature of the human body, this is the core temperature, should always be maintained between about 35 to 39 degrees centigrade. Okay, so beyond that, it is not recommended, or it could become dangerous to the human being. So as I have already explained, when the temperature is lower than 35 degrees centigrade or higher than 39 degrees centigrade, then people suffer major loss in efficiency. It becomes lethal when the temperature falls below 31 degrees centigrade or rises above 43 degrees centigrade. Now let us look at the heat balance equation. Let us see what decides the temperature of a human body, how the temperature of a human body varies. Okay. So for that we have to understand a heat balance equation for a human being. The temperature of a human body depends upon the thermal energy balance between itself and the surrounding thermal environment. As I said, the human body can be considered to be a heat engine. So you can apply the conservation of energy to a human body. You can take the human body as a control volume, and you can apply energy balance. If you apply thermal energy balance, this is what is known as heat balance. Okay, what do we get? So when we apply this, we get what is known as a heat balance equation. This heat balance equation for a human body is given like this: Qzen is equal to Q subscript Fk plus Q subscript Res plus Q subscript St, where Qzen is the rate at which heat is generated in the body. That should be equal to Qsk. Qsk is nothing but total heat transfer rate from the skin, plus Q subscript Res, which stands for heat transfer rate due to respiration, plus Q subscript St. Q subscript St, as you can see, stands for the rate at which heat is stored inside the body. That means this is a very simple energy balance equation. The rate at which heat is generated inside the human body should either be rejected or it is stored. Okay, because it has to be conserved, right? Now let us look at each of these terms. The first term is the heat generation rate. The heat generation rate Qzen is given by Qzen is equal to m into 1 minus eta, where m is the metabolic rate and eta is the thermal efficiency. As I said, for most of the applications or for most of the common tasks, this thermal efficiency term is almost close to 0. So you can neglect it. If you neglect it, you find that the heat generation rate is equal to the metabolic rate m. Okay. And the metabolic rate, on what does it depend? The metabolic rate depends on the activity, okay, the human activity, and it is measured in the unit met. Okay, this is a new unit. The metabolic rate of a human being is measured in a unit called met. And what is a met? A met is defined as a metabolic rate per unit area of a sedentary person. Sedentary person means a person who is sitting quietly, okay, without doing any activity. So a met is defined as a metabolic rate per unit area of a sedentary person, and it is found to be equal to about 58.2 watt per meter square. Okay, this is also known as basal metabolic rate. Now let us the metabolic rates, for as I said, the metabolic rate depends very much on the human activity. Okay, so people have conducted several experiments and they have determined the metabolic rates for a wide variety of activities. As I said, why do we need the metabolic rate? Because the metabolic rate finally becomes a load on the cooling system. So we have to have a knowledge of this. That is the reason why people have determined the metabolic rates. This data is available, for example, in ASHRAE handbooks. So let me show some typical metabolic rates. This table shows typical metabolic rates. Here we have the activity, then the specifications of the activity and the metabolic rate. And as I said, the metabolic rates are expressed in the units of met. For example, if a person is resting means, let us say he is sleeping, then the metabolic rate is about 0.7 met. If he is reclining means he is okay, then the metabolic rate is about 0.8 met. And if he is seated quiet, as I said, the metabolic rate is 1 met. In fact, this is the definition of met. And if he is standing in a relaxed manner, metabolic rate is 1.2 met. Like that you can see the metabolic rates for different activities, for example for walking, for office activity, for driving, domestic activities, dancing, teaching, games and sports, etc. Okay, you can see that for domestic activities the metabolic rate is quite high. Okay, it is about it can vary from about 1.6 to 3.4 met depending upon the specific activity. You can also see that for very strenuous activities such as wrestling or playing basketball and all, the metabolic rates are very high. Okay, it is as high as about 8.7 met in case of wrestling. This kind of data is available in ASHRAE handbooks for more number of activities. Okay, so one can use the handbooks for getting this kind of a data. Okay. Since the metabolic rate is specified per unit area of the human body, when we say unit area of the human body, normally it is referred to the unclothed or naked body. So, it is essential to estimate the area to calculate the total metabolic rate. You have seen that the metabolic rates are specified in terms of met, and met itself is defined in terms of watts per meter square. Okay, that meter square in the denominator refers to the surface area of the human body. Okay, so if we want to find out what is the total heat rejected from the human body, then we have to know not only the metabolic rate, but we also have to know what is the surface area from which the heat dissipation is taking place. Okay. So, we have to calculate the surface area of a human body. How do we do that? So, people have found empirical equations for the surface area of human body. This is a famous equation called as the Du Bois equation. This equation relates the surface area of a naked human body to its mass and height. Okay, so if you know the mass and height of a human being, you can calculate its surface area. Okay. So, for calculation purposes, the human body is considered to be a cylinder with uniform heat generation and dissipation. Actually, the human body is very complex. Okay, so it is very difficult, in fact, it is almost impossible to model a human body perfectly. Okay. So, but for calculation purposes, you have to make certain assumptions. In an actual human being, the heat generation takes place in a very non-uniform manner. Okay, that means heat generation throughout the body is not same, right. Similarly, the heat dissipation is also not same throughout the human body. Okay, but to take all these effects into account is very difficult theoretically. So, what is done in theory is we assume that a human being is like a uniform cylinder, and the heat dissipation and heat generation of this human being is uniform. Okay. So, under this assumption, the surface area over which the heat dissipation takes place is given by, as I said, this Du Bois equation. The Du Bois equation gives the surface area A subscript du. This is equal to 0.202 m to the power of 0.425 multiplied by h to the power of 0.725. Here the area, this is in meter square. Okay, area is in meter square. M, as I said, is the mass of the human being. This is in kgs, and h is the height in meters. Okay, so you can see that this is an empirical equation. Since the area given by Du Bois equation refers to a naked body, a correction factor must be applied to take the clothing into account. So, this correction factor, defined as the ratio of surface area with clothes to surface area without clothes, has been determined for different types of clothing, and these values are available in ASHRAE handbooks. Thus, from the metabolic rate and the surface area, one can calculate the amount of heat generation Qgen. Okay. So, the procedure for calculating what is the heat generation is that, first of all, depending upon the activity, you have to find what is the metabolic rate in watt per meter square using the data books. Then, depending upon the mass and height, one can calculate what is the area of the body. Okay. So, if you multiply the metabolic rate into the area, that will give you the total amount of heat transferred, but this area refers to the unclothed body. So, we have to take the effect of clothes into account. So, we have to multiply this heat transfer rate into a correction factor which considers the effect of clothing. So, for correction factor, again one has to look at data books such as the ASHRAE data books, where the correction factor for different types of clothing is given. Okay. So, then you have to take the correction factor and multiply that correction factor by metabolic rate and the area, which will finally give you the heat generation rate. Okay. Now, let us look at the second term, that is the total heat transfer rate from the skin. This is given by Q skin is equal to plus or minus Q convective plus or minus Q radiative plus Q evaporative. Here you can see that this Q convective is the heat transfer rate due to convection, Q radiative is the heat transfer rate due to radiation, Q evaporative is heat transfer rate due to evaporation. So, for the heat transfer rate from the skin of a human being takes place by these three modes, that is first is by convection, the other one is by radiation, and the third mode is by evaporation. In the equation it is shown that convective and radiative terms could be either plus or minus. That means the convective heat transfer from a human body can be either from the body to the surroundings or from the surrounding to the human body. When it is from the human body to the surroundings, we use this sign plus. Okay, that means it is positive when the human body is losing heat. When he is gaining heat, it becomes negative. Okay, so the convective and radiative heat transfers can be positive or negative. For example, the convective heat transfer can be negative when the ambient temperature is higher than the human body temperature. Okay, whereas the evaporative heat transfer, that is Q evaporative, is always positive. That means a human being always loses heat by evaporation. And there is another difference between these two and the evaporative heat transfer. The convective and radiative heat transfers are sensible in nature, whereas the evaporation heat transfer is latent in nature. Okay. Using the principles of heat and mass transfer, expressions have been derived for estimating the convective, radiative and evaporative heat transfer rates from a human body. As it can be expected, these heat transfer rates depend on several factors that influence each of the heat transfer mechanism. So, if you look at advanced books on air conditioning or on thermal comfort, you will find that people have derived empirical equations for estimating the convective heat transfer and radiative heat transfer and evaporative heat transfer from a human being. Okay, so using those equations, one can calculate the heat transfer rates, different heat transfer rates. But since all these heat transfer modes depend upon several factors such as what is the air velocity, what is the air drivable temperature, what is the humidity of the air, etc., one has to take all these factors into account. In fact, the empirical equations do take these factors into account. Okay, so you must note the complexity in evaluating all these parameters. Okay, as that is the reason you really don't have a perfect analytical theory or an analytical model. So, most of the time all these parameters are estimated based on experiments. Okay. Now, let us look at the heat transfer rate due to respiration. The heat transfer rate due to respiration is given by Qres is equal to C respiration plus E respiration, where C subscript RES stands for dry heat loss from respiration and E subscript RES stands for evaporative heat loss from respiration. What is this heat transfer rate by respiration? So, you know that all the human beings inhale air and exhale air. So, the air that you breathe in is at a condition same as that of the surrounding air. That means, when you breathe air inside, the air enters into the body at a temperature equal to the surrounding ambient temperature, and the moisture content also will be same as the surroundings. But the air that you breathe out, that means the air that you exhale, that will be at that is considered to be at the temperature equal to the core temperature of a human body. Okay. Similarly, that air that you exhale is treated as saturated. Okay. So, you take in ambient air and you exhale air which is at core temperature and which is saturated. So, in this process a human body can gain or lose heat. For example, outside air is cold, let us say outside air is 20 degrees centigrade and it is very dry. So, when we are inhaling that air, so we are inhaling cold and dry air, and what we are exhaling is warm air and humid air, because the core temperature is about 37 degrees. So, the air that is coming out of the body is at 37 degrees centigrade and it is also saturated. Okay. So, in this process of inhaling cold and dry air and exhaling warm and humid air, a body loses heat. Body loses both sensible heat as well as latent heat. Okay. This is one example. In another case, for example, outside air is very hot. So, when the air that you inhale will be hotter than the air that you exhale. So, in this process body gains heat. Okay. So, this sensible heat loss or sensible heat gain because of this respiration process is known as dry respiration heat transfer, heat loss or gain. Okay, and the heat gain or loss because of the evaporation is known as evaporative loss. You will find that the dry, as I said, the dry loss is sensible, whereas the evaporative loss is latent. And most of the cases the evaporative loss is always a loss. That means the body always loses heat by evaporation, whereas the body can gain or lose heat by sensible heating or cooling. Okay. Again, correlations are obtained for heat losses due to respiration in terms of metabolic rate, ambient conditions, etc. And the heat transfer rate due to respiration can be significant. Okay. And as you can guess, this depends upon what is the respiration rate, what is the rate at which you are taking in air and what is the rate at which you are breathing out the air. And the last term, that is Q storage. For comfort and ultimately for survival, the rate of heat stored in the body, QST, should always be 0. That means a body should neither store heat nor should lose heat, because the body, as I said, its temperature should be maintained at a fixed point. Okay. So, there should not be either heat accumulation or continuous heat loss. That means the QST should be 0, and this should be 0 at neutral condition. And it is found that a sedentary person at neutral condition loses about 40% of heat by evaporation, about 30% by convection, and about 30% by radiation. So, you can see that the evaporation loss is quite high. However, this proportion may change with other factors. For example, the heat loss by evaporation increases when the dry bulb temperature of the environment increases. Okay. So, if you look at what is the mechanism by which a body loses heat when outside is very hot. Let us say in a typical summer, outside temperature is 45 degrees centigrade. Okay. When outside temperature is 45 degrees centigrade and a body has got to be maintained at 37 degrees centigrade. So, body cannot lose heat by convection or radiation. Okay. In fact, the body gains heat by convection or radiation, because the temperature of the outside is greater than the temperature of the inside the human body. Okay. So, body gains heat by convection and radiation. So, whatever heat it is gaining, it has to lose over and above the heat that is being generated in the human body. So, how it can lose? So, the only way it can lose this heat is by evaporation. Okay. That is why we perspire. In fact, I will explain this a little later. Okay. So, the body has to lose heat by evaporation. We sweat when the temperature is higher outside, and due to this sweating there will be an increased amount of evaporation. As a result, we lose more amount of heat. Okay. So, what I am trying to say is the percent by which a human body loses heat does not remain fixed, it varies from condition to condition. Okay. Since the body temperature depends on the heat balance, which in turn depends on the conditions in the surroundings, it is important that the surroundings should be such that the body is able to maintain the thermal equilibrium with minimum regulatory effort. Okay. So, in fact, I was talking about the neutral condition and thermal equilibrium and all. Basically what it means is that without much effort or without any effort, a body should be able to lose heat. Okay. It should not make any extra effort to lose the heat that is being generated inside the body. So, that is known as the neutral condition. Okay. But all living beings, including human beings, have certain regulatory mechanisms inside the body. Okay. These are all inbuilt regulatory mechanisms, which will try to maintain the body temperature when the outside conditions are not favorable. Okay. That means when the outside becomes colder or hotter than the neutral condition, then this regulatory mechanism comes into picture, and it will try to maintain the body temperature by initiating certain processes. Okay. So, as I said, all living beings have inbuilt regulatory processes against cold and heat, which to some extent maintains the body temperatures when the external conditions are not favorable. Human beings consist of a thermoregulatory system. Now, let me quickly explain what is this thermoregulatory system and how does it work. So, what happens when the environment temperature is colder than neutral zone? So, what happens when the outside temperature is cold? We know from experience that when the outside temperature is cold, we lose more heat than is being generated. Okay. So, that means the heat generation inside the body is less and heat loss is more. Okay. So, momentarily you will find that body will tend to lose temperature Okay, that means its temperature tries to go down, but the thermoregulatory mechanism of the body will try to prevent this. So it fights this effect in different steps. Okay, the first step is like this. When the outside temperature is cold, the first action is what is known as zone of vasomotor regulation against cold. This is also known as vasoconstriction. So what happens during this process is that the blood vessels adjacent to the skin constrict. So what happens because of this? Because of this, the flow of blood to the outer skin is reduced. Once the flow of the blood is reduced, heat transfer to the immediate outer surface is reduced. Okay. As a result, the outer skin tissues act as insulators. Okay. So basically, how heat is lost from the core of the body to the surroundings? The blood acts as a carrying agent. Okay. As you know that blood continuously circulates through the human body. So the blood carries the heat from the inside of the core of the body, and it brings the heat to the surface, that means to the skin, and from the skin heat is lost to the surroundings. Okay. So when the outside temperature is low, body is losing more heat. Okay. That means this heat loss has to be reduced. So what the regulatory mechanism does is it constrains the blood vessels. Okay. That means blood vessels become constricted, or they become smaller or narrower. When they become narrower, less blood flows to the outer skin of the body. Okay. When less blood flows to the skin, less amount of heat is carried from the core of the body to the skin. Okay. Since less heat is carried, less heat is lost. Okay. So this is the first step against the cold. So during this process, the outer skin or the tissues of the outer skin act as insulators, and they prevent the heat loss. But if the temperature drops further, then vasomotor regulation does not provide enough protection. Okay. Then the body enters into what is known as zone of metabolic regulation. In this zone of metabolic regulation, a spontaneous increase of activity is initiated, and this is nothing but the shivering. Okay. So we start shivering when the temperature falls down. What happens due to shivering? Because of the shivering, since the activity is increasing, body heat generation is increased. Okay. That means temporarily we increase the generation of heat to take care of the increased heat losses. Okay. So when the losses are increasing, the only way it can combat these losses is to increase the heat generation. That is the reason why we have to eat, people say that you have to eat food, good food in winter, so that energy can be, there is sufficient energy which will take care of the increased losses. Okay. So if the temperature falls further, if the temperature drops further, then the body is not able to combat cooling of its tissues. Okay. So as I said, to a certain extent only the thermoregulatory mechanism can work. Beyond a certain point, it cannot simply work. Okay. So it starts failing. So what happens if the temperature drops further? If the temperature drops further, the body enters into what is known as a zone of inevitable body cooling. That means the regulatory mechanism cannot do anything. Okay. So there will be continuous loss of heat from the body. As the heat is being lost, your Q storage term in the heat balance equation becomes positive, it becomes negative. That means body temperature starts dropping. Okay. So this is what is known as zone of inevitable body cooling. Okay. And as we have seen, if the body temperature falls below say 31 degrees or so, it can become lethal. Okay. So this has got to be prevented. So this is the action of the regulatory mechanism against cold. Let us see how the body fights the heat. When the environment is hotter than the neutral zone, as you know, when the environment is hotter than the neutral zone, less heat is lost and more heat is generated. Okay. That means generation is more compared to the loss. Once generation is more compared to the loss, the Q storage term becomes momentarily positive. That means body starts accumulating or storing heat. Once body starts storing heat, its temperature again tries to increase. When again temperature starts increasing, the thermoregulatory mechanism comes into picture. So what does it do? First thing it does is it initiates an action, and the body enters into what is known as a zone of vasomotor regulation against heat. This is exactly opposite to the zone of vasomotor regulation against cold or vasoconstriction. Unlike vasoconstriction, when the external temperature increases, the blood vessels adjacent to the skin dilate. That means they become larger. Once they become larger, the flow of blood and transport of heat to the outer surface increases. Okay. So the outer skin temperature increases because of this, providing a greater temperature for heat transfer by convection and radiation. Okay, since less heat is being lost because of the smaller temperature difference available for heat loss, what the body does is it pumps more blood to the outer skin. Okay, once more blood is pumped to the outer skin temperature increases, because more blood flow means more heat flow, right. Then the outer skin temperature increases means larger delta T is available for heat loss from the outer skin. Okay, so this is the first step. The second step is what is known as zone of evaporative regulation. If environmental temperature increases further, the sweat glands become highly active, drenching the body surface with perspiration. If the surrounding air humidity and air velocity permit, then increase in body temperature is prevented by increased evaporation. This also we normally experience on a hot day, when the outside temperature becomes very high, then the vasodilation is not sufficient. Some other mechanism should come into picture so that body can reject heat. This mechanism is what is known as zone of evaporative regulation. Okay, that means the outer surface of the body, that is the skin of the outer skin of the body, is covered with perspiration. Okay, this is achieved by triggering the sweat glands. Okay, the regulator mechanism triggers the sweat glands. The sweat glands start sweating more. Okay, so you have lot of water on the outer surface of your body. If the outer surface humidity is low and if there is sufficient air velocity, then the water that is accumulated on the outer surface of the human body can evaporate. Okay, since evaporation is a latent heat transfer process, lot of heat can be transferred during this process. The body temperature can be maintained within the required limits by the process of evaporation. Okay. Now, if the temperature increases further and the outside conditions are not favorable, then the body enters into what is known as the zone of inevitable body heating. Just like zone of inevitable body cooling, during this zone the body temperature increases, leading to the zone of inevitable body heating. Okay, that means body temperature starts increasing. Increase in internal body temperature leads to several ill effects. This could be very, very dangerous. The first ill effect is what is known as heat exhaustion. The symptoms of this heat exhaustion is fatigue, headache, dizziness, irritability, etc. Of course, heat exhaustion is not dangerous or lethal, because a person can recover from this. Okay, if he takes rest in a shadow or in a shade. The second problem is heat cramps. Heat cramps means basically loss of body salts due to increased perspiration. Okay, whenever the body is losing water by perspiration, along with the water, salt also is lost. Okay, once the body loses too much of salt, then it goes into what is known as the heat cramp. Okay, it feels the heat cramps. Heat cramps, in fact, you might have seen that typically cricket players or football players, when they play cricket or football under hot conditions, they experience this. Okay, because when they are playing the games, their activity level is quite high, so they have to lose a lot of heat, because a lot of heat is generated inside the body. So all that heat generated has to be lost. So they cannot lose all that heat just by convection or radiation. Okay, so they have to lose. They will be losing most of the heat by evaporation. Okay, that means they will be losing lot of water. So along with this water, they also lose salts, body salts. Okay, if the body salt loss is very high, then they experience this heat cramps. Okay, so the remedy for this heat cramp is they have to take some salt tablets and take some rest. Okay, so that again the body gains the salt, right. The third ill effect, which is most dangerous, is known as heat stroke. Heat stroke could cause permanent damage. It's very dangerous, and it can lead to the damage of the brain, or it could even be lethal. That means it could even cause death if the body temperature exceeds 43 degrees centigrade. Okay. So this is the thermoregulatory system and how it works. Thus, it is seen that even though human body possesses a regulatory mechanism, beyond certain conditions it becomes ineffective. Hence, it is essential to ensure that surrounding conditions are conducive for comfortable and safe living. Okay, so you cannot simply rely on the thermoregulatory mechanism. Okay, it cannot take care forever. So outside conditions also must be conducive. If the outside conditions are not conducive, then an air conditioning system will be required to provide the required conditions. Okay, these conditions are required first of all for comfort, and second for survival also. Okay. The purpose of comfort air conditioning system is to provide suitable conditions in the occupied space so that it is thermally comfortable to the occupants. Now let us look at the factors affecting thermal comfort. The first factor is what is known as physiological factors. The physiological factors are age, activity, sex and health. These factors influence basically the metabolic rate. It is observed that of all these factors, the most important is the activity. Other factors are found to have negligible effect on thermal comfort. That means factors like age and health do not have significant effect. The second factor affecting thermal comfort is what is known as insulating factor due to clothing. Okay, because all the human beings wear clothes, and clothes act as insulation. Okay. So this type of the type of clothing has strong influence on the rate of heat transfer from the human body. Okay, so this is important. The unit for measuring the resistance offered by clothes is called as clo. So just like met for metabolic rate, people have defined a unit for measuring the resistance of the clothes, and this unit is called as clo. Okay, so let me briefly explain what is this clo. 1 clo is equal to a resistance of a heat transfer resistance of about 0.155 meter square Kelvin per watt. Okay. Typical clo values for different types of clothing have been estimated and are available in the form of tables, for example in ASHRAE handbooks. For example, a typical business suit has a clo value of 1, okay, while a pair of shorts has a clo value of about 0.05. Obviously, higher the amount of clothes you wear, the resistance offered by the clothes also increase. Okay, when you wear minimum clothes, then the resistance offered by the clothes will be less. Sometimes the unit tog is also used for measuring resistance of clothing. Of course, clo is more common. 1 tog is equal to about 0.645 clo. Now let us look at the third and most important factor, that is known as the environmental factor. The environmental factors are dryable temperature of air, relative humidity or moisture content of air, air motion or air velocity, and finally the surrounding surface temperature. So what is the effect of these factors? The dryable temperature affects heat transfer by convection and evaporation. Relative humidity affects heat loss by evaporation. Air velocity influences both convective and evaporative heat transfer, and the surrounding surface temperature affects the radiative heat transfer. Apart from the above, factors such as drafts, asymmetrical cooling or heating, cold or hot floors also affect the thermal comfort. The objective of a comfort air conditioning system is to control the environmental factors so that the comfort conditions prevail in the occupied space. The typical air conditioning system has no control on the physiological and insulating factors. However, suitable clothings may help in reducing the cost of the air conditioning system. Okay, so by providing an air conditioning system, what is that you can control? You can control only the environmental factor. That means you can control the dryable temperature, moisture content, air velocity inside the conditioned space. Okay, you cannot control, or you have no control on the physiological factors such as age. You cannot decide what should be the age of the occupant. Okay, similarly, you also do not have any control on the activity, right? Of course, air conditioning system or the air conditioning system designer has no control on the clothing, but it is seen that by wearing or by suggesting suitable clothing, one can reduce the cost of an air conditioning system. Now let us look at indices for thermal comfort. Important factors which affect thermal comfort, as we have seen, are the human activity, clothing, air dryable temperature, relative humidity, air velocity and surrounding temperature. Since so many factors are involved, many combinations of the above conditions provide comfort. There is no unique combination, there are many combinations possible, all of which will give equal amount of comfort. Hence, to evaluate the effectiveness of the conditioned space, several comfort indices have been suggested. These indices can be divided into direct and derived indices. So how do you estimate? For example, you have got an air conditioned building. Okay, you wanted an air conditioning building and you have got an air conditioned building. How do you know that it is good or bad? Okay, how do you evaluate the effectiveness of an air conditioned building? So, the effectiveness of an air conditioned building ultimately depends upon the thermal comfort, okay, whether it is providing thermal comfort or not. And as we have seen that the thermal comfort depends on several factors. Okay, so all these factors will affect the thermal comfort. Okay, so in order to judge the effectiveness of an air conditioned building, all these factors must be considered. Since so many factors are involved, as I said, a combination of many combinations of these factors can give you comfort. Okay, so to measure basically the effectiveness of conditioned space, people have devised the comfort indices. Okay. The direct indices are dry bulb temperature, humidity ratio, air velocity and mean radiant temperature. We know dry bulb temperature, humidity ratio and air velocity. Mean radiant temperature is a new parameter and this is defined as the mean radiant temperature T subscript MRT is defined by this equation. T MRT to the power of 4 is equal to Tg to the power of 4 plus Cv to the power of half into Tg minus Ta, where Tg is called as the globe temperature, Ta is the dry bulb temperature, V is the air velocity and C is a constant whose value is equal to 0.247 into 10 to the power of 9. Here all the temperatures are in absolute Kelvin scale, velocity is in meter per second and dry bulb temperature is also in Kelvin, okay, as I have already mentioned. What is this globe temperature, by the way? This globe temperature is the temperature measured at steady state by a thermocouple placed at the center of a black painted hollow cylinder of 6-inch diameter kept in the conditioned space. This is given in Kelvin. The reading of thermocouple results from a balance of convective and radiative heat exchanges between the surroundings and the globe. So, that is how the globe temperature is measured, which is related to the mean radiant temperature or the surrounding surface temperature. The derived indices combine two or more direct indices into a single factor. Important derived indices are effective temperature ET, operative temperature TOP, heat stress index HSI, predicted mean load PMV, percent of people dissatisfied PPD, etc. Now, let us define effective temperature ET. This effective temperature combines the effects of dry bulb temperature and relative humidity into a single factor. It is defined as the temperature of the environment at 50% RH, which results in the same total heat loss from the skin as in the actual environment. So, this is the definition of effective temperature. Since the value depends on other factors such as activity, clothing and air velocity and T mean radiant temperature, a standard effective temperature is defined for the following conditions. That means standard effective temperature is defined for a clothing value of 0.6 kilo, activity of 1 met, air velocity of 0.1 meter per second and the mean radiant temperature is taken as same as the dry bulb temperature. Now, the operative temperature, this factor is a weighted average of air dry bulb temperature and mean radiant temperature. That means basically it combines the dry bulb temperature and the surrounding surface temperature. This is given by TOP is given by this equation. Okay, HR into T MRT plus HC into T ambient divided by HR plus HC, where HR is the radiative heat transfer coefficient which we have defined earlier and HC is the convective heat transfer coefficient. T MRT is the mean radiant temperature, T ambient is the ambient dry bulb temperature. And if HR and HC are almost same, then the operative temperature is almost equal to the arithmetic average of mean radiant temperature and the ambient dry bulb temperature. Okay. ASHRAE has defined a comfort chart based on the effective and operative temperatures. Okay, let us look at this ASHRAE comfort chart. The comfort chart shows the recommended inside conditions for summer and winter, because this is the ultimate objective of this lecture, okay, to find the required inside conditions for summer and winter air conditioning systems. Okay. The comfort chart is based on statistical sampling of a large number of occupants with activity levels less than 1.2 met. Okay. This is valid for this kind of activities. This picture shows the ASHRAE comfort chart. This looks almost similar to a psychrometric chart, but here what you have on the x axis is the operative temperature, not the reliable temperature. On the y-axis you have the humidity ratio, and the effective temperature lines are shown here. This is the 20 degree centigrade effective temperature line, this is the 22.5 degree centigrade line, this is 23.5 degree line, and this is the 26 degree centigrade line. And you also see the 60% RH line and 2 degree dew point temperature line. This is the 2 degree dew point temperature line. Okay, and here some areas are hatched areas are shown, and this blue zone, okay, all this blue zone is a recommended comfort condition for winter. Okay, that means if you are inside conditioned space, life anywhere here during winter, then the conditioned space will be comfortable. Similarly, for summer, this red hatched area is the recommended zone for summer. Okay, that means if your condition lies somewhere in the red zone, then the condition space will be comfortable during the summer. And you can see that there is some area which is being overlapped. There is an overlapping area for winter and summer zones. Okay, so if the conditioned space in this lies in this overlapping zone, then a person wearing summer clothes will feel slightly cooler, and a person wearing winter clothes will feel slightly warmer. Okay. So this is the comfort chart, as I said, and you can say, you might have noticed that the comfort zones are bounded by effective temperature lines, a constant relative humidity line of 60% and dew point temperature of 2 degrees centigrade. The upper and lower limits of humidity, that is 60% relative humidity, which is the upper limit, and 2 degrees centigrade dew point temperature, are based on the moisture content related considerations such as dry skin, eye irritation, respiratory health and microbial growth. Okay, all these problems are related to the moisture content. Okay, so these upper and lower limits for humidity are based on these considerations. Now, based on the chart, ASHRAE makes the following recommendations. Recommended inside design conditions for winter: the operative temperature between 22 to 23.5 degrees centigrade at a relative humidity of 60%. T operative between 20.5 to 24.5 degrees centigrade at a dew point temperature of 2 degrees centigrade. Inside design conditions for summer are like this: T operating temperature between 22.5 to 26 degrees centigrade at a relative humidity of 60%, and T operative between 23.5 to 27 degrees centigrade at a dew point temperature of 2 degrees centigrade. So you might have seen that when the air humidity is lower, then you can maintain the conditioned space at a slightly higher temperature. Okay, when the humidity is higher, then the required temperature will be lower. Recommended comfort conditions for different seasons and clothing at 50% RH, air velocity of 0.15 meter per second and an activity level of less than 1.2 met are given in this table for different season, as I said. For example, in winter, okay, if a person is wearing heavy slacks with long sleeve shirt and sweater, that means it has a clothing resistance of 0.9 kilo, then the optimum operative temperature should be about 22 degrees centigrade. But the temperature can vary from 22 to 23.5 degrees centigrade for 90% acceptance. Okay. Similarly, in summer, if a person is wearing light slacks and short sleeve shirt which has a clothing resistance of 0.5 kilo, then the optimum temperature required is about 24.5 degrees centigrade. But this can vary from 23 to 26 degrees centigrade with 90% acceptance. Now you can see the effect of clothing. If he is wearing minimal clothes, that means let us say shorts, which has a resistance of 0.05 kilo, then the optimum operative temperature becomes quite high, okay, 27 degrees centigrade, and the range will be 26 to 29 degrees centigrade. So these are the recommendations, and based on these values one can maintain or one can decide the required inside conditions for a conditioned space for both summer as well as winter air conditioning systems. Okay. To minimize cost, air conditioning system should be operated at as low temperature as acceptable in winter and as high a temperature as acceptable in summer. For summer, the inside temperature can be higher for places closer to the equator. 1 degree centigrade rise in effective temperature is allowed for each 5 degree reduction in latitude with reduced clothing and increased air velocities. The required conditions change if the activity levels are different. For example, in a gymnasium, the required temperature may be much lower than what is recommended for low activity. And P.O. Fanger, Professor Fanger of Denmark, has carried out extensive pioneering studies in this area, and he has made recommendations for several conditions. So basically, one thing you must keep in mind is an air conditioning system involves cost, both initial as well as running cost. So if you want to minimize this cost, then the temperature, inside temperature, should be as high as possible in summer, and it should be as low as possible in winter. Okay. Of course, within the certain guidelines or within certain acceptable ranges. Okay. So how this can be done? For example, in summer, as I said, the inside temperature should be as high as possible. So people should preferably wear light clothes. Okay. If people are wearing heavy clothes in summer, then required temperature in the conditioned space will be very low. Once the required temperature becomes very low in summer, then the cost of the air conditioning system becomes high. Okay. Similarly, the required temperature can be increased by slightly increasing the air velocity. That means at higher air velocities, required temperature also increases. Thereby, you can reduce the cost of the air conditioning system. Similarly, the optimum temperature also is found to vary from location to location. That means for people living in hotter areas, the optimum temperature for summer air conditioning system can be slightly higher compared to people living in colder areas. Okay. Based on the studies of Fanger and subsequent sampling studies, ASHRAE has defined a thermal sensation scale. Using the thermal sensation scale, expressions for predicted mean vote and percent people dissatisfied have been obtained. So these are all more advanced thermal comfort indices. And these studies show that even when heat balance is established, that means even when you maintain the neutral condition, at least 5% of the occupants show dissatisfaction with the thermal environment. That means it shows that when you are conducting the studies with 1000 people, at least there will be 50 people who say that they are not happy with the surroundings. Okay, that means it is not possible or it is impossible to satisfy all the occupants. Okay, even when everything is perfect, right? This is based on the sampling studies obtained at several places. Okay. And the details of these studies and these indices such as PMV and PPD are available in ASHRAE handbooks. Okay, one can look at ASHRAE handbook, or one can read the excellent book on thermal comfort written by Professor Fanger. Okay, so with this I end this lecture. Let us conclude what we have studied in this lecture. In this lecture, the following topics are discussed: criteria for selecting inside design conditions, thermal comfort, heat balance equation for human beings, factors affecting thermal comfort indices, ASHRAE comfort chart, and recommended inside design conditions for winter and summer. In the next lecture, we shall look at how to select the design outside conditions. Thank you.